When we were looking at transverse waves on strings, we looked at standing waves and said, here is an example of resonance. Then we switched over to doing sound, and now we are going to talk about resonance again. When we did these transverse waves, we said we have a string like this, and we'll give this thing a length L. And the big thing that we needed to worry about was our boundary conditions. We said if this was fixed on both ends, if this was fixed, then our resulting wave that could fit on here needed to have a node at a fixed end. Same thing here. Fixed, meaning held in place, we get a node. And that let us put waves on here. Right, we could do a wave like this, and we looked at the loops and said this is like our n equals 2 wave, or we could do a wave like this. And have this be our n equals 3 wave. And the big thing really we needed was to look at those boundary conditions. Now in the last video, we looked at these sound waves, and the sound waves were compression waves, and that made things a little bit difficult, but when we were able to plot what was going on, like as a graph, then we could see some things that looked really familiar. Let's say I'm going to look at maybe some kind of a tube. Now, if I want to put a sound wave in this tube, I need to, again, think about my boundary conditions. Those are important. I want to plot this, and I want to plot sound displacement. The reason I'm doing this is because it lets me take a compression wave and turn it into something that's a whole lot easier to see. The sound displacement, I can take the sound, the air particles that are inside this tube, and I can move these a long way. This is an open end of a tube, and it turns out that an open end of a tube, what I need is a displacement antinode. So I need to start on an antinode. This is open also, so I need to end on an antinode. So maybe I've got a wave that looks like this. I start on an antinode, I end on an antinode. Now if I were to count my loops, back here I would have said here's one loop, and here's another loop. That's why I get my n equals 2. I'm going to do the same thing here. Here's one loop, here's a half a loop, and here's a half a loop. So I have 2 complete loops. This is my n equals 2 wave. I could also go from antinode to antinode to antinode and back up. Now I've got 1, 2, a half, so that is my n equals 3. So where I have, again, a length of L, back here with my string, what I was able to say is that the wavelength of my nth harmonic was going to be 2 times the length of my string divided by n. So when n equals 2, my wavelength is L. 2 times L divided by 2. When my wavelength, or when my n is 3, my wavelength is 2/3 of L. 2 times L over 3. I get the same thing here. When my wavelength, my index is 2, my wavelength, I have one loop and a second loop. Remember, 2 full loops equals 1 wave, so then my wavelength is L, 2L over 2. When my n is 3, I have 1, 2, 3 full loops, so 2 loops is 2/3 of the length, 2L over 3. So 2L over N is my lambda N, and my sound displacement mathematically looks, for a pipe, mathematically looks exactly the same as my standing waves on a string. Just instead of going node to node, I'm going antinode to antinode. There's a little bit more. I get that my sound displacement wavelengths are 2L over N like before, which means my wavelengths and frequencies are going to work the same way, so I'm going to get an N times my fundamental wavelength, or frequency. Wavelength times frequency still has to give me a wave speed, and now that I'm dealing with air, this will be 340 meters per second in air. So now my wave speed is fixed, and I know that number ahead of time, which means when I encounter a problem about this, I'm probably not going to be given that number. With a tube, I'm able to do something else. What if I take that same tube and now I put a cap on the end? The side's open, and an open end gives me an antinode as the boundary condition. Open and anti both start with vowels, so that's easy to remember. This side I've put a cap on it, so this is now closed, and a closed end needs a node. Now I can start putting waves in here. I'm going to intentionally use different colors than I was using before, just so that we don't start equating them. The biggest wave that I can put in here starts on an antinode, ends on a node. That looks like this. That is half a loop, which means half a loop equals my wave, or equals my full length. One full loop would require 2L, and my wavelength, which is always equal to 2 loops, equals 4L. This is different. Let's keep going. Next one, I can start on an antinode, I need to end on a node, and I've got something going on in between. I can't go directly there because I've already done that one. Now I have one loop and a half loop. I have 3 half loops for L, which means one loop equals 2/3 L. My wavelength, which is 2 loops, equals 4/3 L. This pattern's a little harder. Let's do another. We'll go green. Go up, come down, and back again. And let me get rid of some of these other colors because they start to be really busy. So now I've got this. 1 loop, 2 loops, and a half, so that is 5 half loops. So 1 loop equals 2/5 L. I'm just flipping my fraction, right? My wavelength, which is 2 loops, equals 4/5 L, and I start to get a pattern. Let's see if I can put these together. First, let's throw that over 1, let's throw that over 1. My wavelength, it looks like, is just going to be 4 times L divided by N. My frequency is just going to be N times my fundamental frequency, and my wave speed is still going to be a frequency times a wavelength. But now I can only use odd number N values. So maybe there are good ways of remembering this. Maybe what we see is when we have asymmetric boundary conditions, meaning they don't match. Maybe I can remember that asymmetric boundary conditions are a little weird. They're a little odd. So I'm going to use odd numbers. Symmetric boundary conditions, I get to use my evens and my odds, right? So over here for the symmetric case, I can use all my n values. For the asymmetric case, I am left with just my odd numbers. But other than that, things work pretty similarly. I get a 4L over n instead of a 2L over n. So my wavelength formula changes just a bit, because instead of counting loops, I'm counting half loops. And now I'm stuck with just my odd numbers. I'll do just a tiny bit more with this. When we talk about waves, we talk about these resonances and resonant indices. So we'll call this my resonance index, or maybe harmonic index if you like. And then this is going to be my overtone number. If I have symmetric boundary conditions, I can say this. My resonant index, I can do 1, 2, 3, 4, 5, and so on. The overtone numbers that go with these, so overtones are effectively a count of how many harmonics you are above the fundamental. The first harmonic is 0 overtones above the fundamental. We can't talk about an overtone there. We are now, for n equals 2, we are now 1 above our index, or above our initial. So that's an overtone number of 1, 2, 3, 4, which means my overtone number for the symmetric case, overtone number, is just going to be n minus 1. For the asymmetric case, it's just a little different, because everything's just a little different. I can use indices 1, 3, 5, 7, 9. I can't use my even numbers here. So when I write these out, and now I want to look at my overtone numbers. First one, it doesn't count as an overtone. It can't be. It's not over anything. This is my first overtone. This is my second overtone, third, fourth. So now my overtone number is, it's still how many indices, available indices, I am above my fundamental, but it doesn't line up the same way. So when I'm talking about, I've got this tube, and I want to activate the third overtone, and it's open on both ends. What am I doing? I'm looking at the n equals 4 harmonic, right? So if I want the third overtone for this guy, I would say third overtone. All right, that's my n equals 4 harmonic. I can say my wavelength 4 is 2L over 4 equals L over 2, and I've got that. If I want my third overtone after I put a cap on this thing, third overtone now is my n equals 7 case. I'm at lambda 7, and that's going to be 4L over 7. I had an L over 2, I'm now at a 4L over 7. I'm looking at a completely different situation, right? third overtone here is the n equals 4. That's the for loop, so I've got like a something like this. I need to end that a little earlier. I've got something like this, for loops. Down here, I'm at 7 half loops. So I would go 1 half loop, 2, 3, 4, 5, 6, 7. And it'll look like that. Very different waves, different formulas, different everything, just by putting a cap on the one side and switching to my asymmetric mode.